Hi there, folks. Today we're looking at scientific notation. And scientific notation is just a shorthand way of expressing very large or very small numbers. And when we use scientific notation, we do that using powers of 10. Okay, so we're going to use powers of 10 to express really big or really small numbers. Okay, scientific notation is in this form: a times 10 to the nth power. Okay, where n is an integer, something that's either positive or negative, and the a value here has to be between 1 and 10. Okay, it can be equal to 1, but it can't quite be equal to 10. So we have to have a single digit followed by decimals. Okay, that's our only options in terms of scientific notation. So the placement of the decimal point is very important, and then the n value being a positive or negative comes into play a little bit later here. Here's some examples of scientific notation. Notice this first one. We've got an 8.3. Again, it's in that acceptable range between 1 and 10. And now I have 10 to the 5th power. And 5 is an integer, so that works. We can't have fractions up there or decimals in terms of that. But if we look at the next one, again, it's between that 1 and the 10. And we have an n value that's an integer. The last one, 7.1, it's in that acceptable range. And the n value is still an integer, because remember, the integers include negative numbers as well. Okay? If we look at the next couple, we want to state whether or not each of these is in scientific notation. All right, so if we look at the first one, I've got 0.23 times 10 to the negative third. And this one is not in scientific notation because that a value, that number out front, is not in the acceptable range. Okay? Right here, this has to be between 1 and 10, and the 0.23 is not acceptable. We'd have to write it as 2.3. So no, this one is not in scientific notation. If we look at the next one, again, the a value, that first piece, is between 1 and 10, and we've got an integer up here. So this one looks fine. So this one is a yes. This one is in scientific notation because everything's where it should be, and everything's in the acceptable range. And then if we look at the last one, I noticed that this piece looks okay. It's between 1 and 10, so it's in that acceptable range. But over here, instead of having 10 raised to some power, we've got 100 raised to a power, and that's no good. Okay? With scientific notation, we're only using powers of 10, so this one is not in scientific notation. If I look at these guys, if I look at the next one, we want to write each of these in standard form, so we're going to take it out of scientific notation and write it the way we would normally write numbers. Okay, so for this first one, really we can just think of this in terms of its operations. Let's think about this as 5.5 times 10 to the 6th power, which is essentially a 1 with 6 zeros. Okay, and then if I multiplied these out, that would give me a 5 with 5 zeros. Okay? And again, the shortcut here in terms of scientific notation, once you get used to it, is I can go right from here to the answers by thinking of it this way. When I have a positive exponent, the positive exponent tells me to move that many spaces to the right. So in this one, I would move 6 spaces to the right. Okay, so it essentially tells me which way to move my decimal point. And keep in mind, if we have a number, a large number up here, the number's just going to get bigger. Okay, so we move it to the right. If we look at the next one, thinking about this in terms of our rules of exponent, this is a 3.1 times 10 to the negative third. Well, raising something to the negative power, remember, negative exponents mean we flip it to the other side of the fraction bar. So that becomes 3.1 times 1 over 10 to the third, which is 3.1 times 1 over 1,000. And now essentially what's happening here when I multiply fractions, it essentially becomes division. So this becomes a 0.0031. Okay? And again, the other way to think of this, if I wanted to go right from here to my answer, is I could think of this as just moving the decimal point. And since I have a negative exponent, I'm going to move that decimal point. I'm going to move it 3 spaces to the left. Okay? So again, if we remember our rules of exponents, we can easily figure out which way we're supposed to move this thing. But the general rule here is that a positive exponent, I move to the right that many spaces, and a negative exponent, I move to the left that many spaces. So again, in the next one, if I were to go right to the answer here, I would move it 12 spaces to the right because it's a positive exponent. So this would be 4, and then 1, 2. Once I run out of spaces here, I've moved it 2 spaces. I'm going to move it 10 more. So this is 1, 2 spaces, and then 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And all of those spaces I fill in with zeros. Okay, so I fill each of those spaces in with zeros, and now this is my answer. Whew, look at all those zeros. Crazy. Okay. If we take a look at the next one, again, this one I've got a negative exponent if we're using that general rule. The decimal started here, but I'm going to move it 5 spaces to the left this time. I move it 1 space. And again, just like before, I have to add zeros. 2, 3, 4, 5. Okay, so now the decimal is going to end up here, and I have to fill zeros in each of these spaces where I didn't have anything. Okay, let me separate these 2 examples. So my final answer for this one is 0.000071. Okay? So again, scientific notation, we can think of it in terms of our rules of exponents, or we can just think of it in terms of positive exponents, I move it to the right, negative exponents, I move it to the left. If I go the other way, I want to write each of these in scientific notation. The first thing I need to do is decide where the decimal point has to go. Okay, so again, remember, we have to have a value that's between 1 and 10 here. We can equal 1, but we can't equal 10, so it's got to be a single digit with decimals. So I have to decide where am I going to place the decimal point. For this one, I'm going to have to put the decimal point right here and make it look like a 1.43. So if the decimal point is going there, I just need to count how many spaces I need to move it, which is 1, 2, 3, 4, 5, 6, 7, 8, 9 spaces. And after I move it 9 spaces, I'll have a 1.43. And now to express this, it's going to be times 10. And right here, I just have to decide, is this a positive or negative exponent? This one's a positive exponent. Because thinking about putting it back in standard form, I would have to move it back to the right. Okay? You could also think of it this way. Anytime you have a large number, you need a large exponent. Anytime you have a small number, you need a small or negative exponent. Okay? If we look at the next one, in order to place this, again, I need a number between 1 and 10. I can equal 1 but not 10. So I'm going to have to put the decimal point right here after the 1. So when I do that, I'll have 1.0, okay, or just 1. And then it's going to be times 10. Well, now I have to decide how many spaces it's going to move. So I count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 spaces. And again, since I moved it in that direction, since I'm getting a decimal, in order to get back to this decimal form, it's going to have to be a negative exponent. So it's a negative 10. Okay? If I look at the next one, again, I have to place the decimal right here between the 5 and the 1. So this way I have a value that's in the acceptable range. So it's going to be a 5.14. And now I need to count how many places I'm going to move the decimal. 1, 2, 3, 4, 5, 6, 7. So 7 spaces, so it's times 10. And this is going to be a positive 7. Okay? I have to use positives to get the larger numbers. Okay? If I look at the next one, again, I have to place the decimal in the right spot. Here I have to put it between the 3 and the 2, and my arrow got a little off there. Let me try again. There it is. Between the 3 and the 2, that puts it in my acceptable range. That would leave me with a 3.2. And now again, I count. It's 1, 2, 3, 4, 5 spaces. To have something like a decimal, I'm going to need that to be a negative 5 for my exponent. Okay? And these last ones, I've basically taken this map here, and it's asking about the oceans in terms of their square kilometers. And we want to list these from least to greatest. So as I look at these, each being written in scientific notation, I'm going to just copy these down below here so I can take a little bit of a closer look at them. So this first one is the 7.49 times 10 to the 7th. The next one is a 1.41 times 10 to the 7th. The next one is a 1.06 times 10 to the 8th. And then the last one is 1.8 times 10 to the 8th. Okay? And when we look at things in scientific notation in terms of size, in terms of what's going to be the largest and what's going to be the smallest, there's something that kind of determines this a little bit more than others, and it's that exponent. Okay, when I look at this exponent, and I compare an exponent of 7 to something like an exponent of 8 in terms of scientific notation, which of these is automatically going to be bigger when we think of how we move the decimal place? Okay, it's going to be the larger exponent is automatically going to be larger because we're going to automatically have a much larger number because we've moved that decimal point farther. Okay, so right away, just looking at these, I know that the last two over here, these last two pieces, are going to be larger than the first two pieces because they have a larger exponent. Okay, so I know that in terms of the smallest, if I want to go least to greatest, it's between the Indian Ocean and the Arctic Ocean. And really, now that these exponents are the same, I just compare the numbers out front. If I'm moving them the same number of decimal places, really the larger number out front is going to determine which one of these is bigger. So now I know that this first one, the Indian Ocean, is larger than the Arctic. So now I know the smallest value is the 1.41 times 10 to the 7th. Okay, because it has the smallest number out front combined with that smaller exponent. The next one is going to be the 7.49 times 10 to the 7th. Again, it shared that smaller exponent, but it had the larger number out front. Next, when I look at the 8s, these are tied in terms of the value of the exponent. So now I look at the numbers out front. The 1.06 is smaller than the 1.8, so this one comes next. And then the largest one is going to be this last one, the Pacific Ocean, at the 1.8 times 10 to the 8th. Okay? So putting these in order, if we just go ahead and compare these, it looks like the smallest one was the Arctic. The next one was the Indian Ocean. And then the Atlantic. And then the last one was the Pacific Ocean. Okay, so again, when we're talking about the value of these, the exponent determines value more so than the number out front. Okay?